Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a great pleasure to introduce Sergei Artyomov, distinguished professor at CUNY. Sergei built a big group in Moscow, which was leading in provability logics, and now he builds a new group. Probably this is one of central topics, logics of justification. And happy to have you, and welcome, please.
Thank you, Yuri. And it's a big honor to be here, and I wish to thank Microsoft for inviting me for this talk and for supporting fundamental research so generously, so efficiently. So it's a long story which I'll try to cover at long in terms of time span. So we start with some kind of soft philosophical foundational considerations, and we end up with something much more concrete. And in mainstream epistemology, there was a famous tripartite approach to knowledge, and which usually attributed to Plato, who tried to characterize knowledge as justified true belief. And so you see that there are three components that's all tripartite, and the justification is one of the major components in the understanding and the definition of knowledge. And the whole game here is in between belief and knowledge. It's basically answering the question where, if you haven't assume that we understand the notion of belief, and what does it take from belief to count as knowledge? And so the true belief means that belief should be effective. So if you believe in something, that this something, in order to believe to count as knowledge, this something should be true. And also it should be supported by certain justification. Later this account has been questioned, criticized, revised, and now is generally regarded as a necessary condition for knowledge, because there are shown some very tricky examples shown that justified true belief, you can kind of cheat this definition a little bit. So there will be still, you can satisfy justified true belief, which is still not knowledge. So there is a search for some other conditions, and still unclear whether any finite or manageable amount of conditions can really fill in the gap between belief and knowledge.
If I remember this dialogue of Plato, he himself criticized that.
Exactly, yes. Exactly this, yes. But still, he was the one, yeah. And this is a state of art in epistemology. It's a matter of pride to come with something and also to criticize this themselves, and there are many different positions still. But there is certain consensus that justified true belief, it's a necessary condition, but by far not sufficient for being knowledge. However, the main point of this remark is that justifications are in the heart of the discussion. And the traditional logic of knowledge, which can count from, Hintikar, so model, has dominated model logic and formal epistemology. So model logic was the formal language of choice for logic of knowledge, which basically treated F is known as knowledge as modality. It's like some tag or special marker which says that F is known. And this marker is called modality is inserted into a formal logic, say propositional or first order or whatever logic in there. And there is also a model theoretic treatment of it, so via possible worlds. And there is a possible world semantics of knowledge which treats F as known as F holds at all possible epistemic situations. it clearly works one way, because if there is an epistemic situation which the agent cannot distinguish, and F doesn't hold there, then F cannot be known, because knowledge should be effective. On the other hand, and also it's easy, visual, and useful in many cases, and leads to very manageable mathematics, a very transparent notion of creepy models, but misses the mark considerably. What if F holds in at all possible worlds? For example, mathematical truths, say P is not equal to NP, whatever case it holds. But the agent is simply not aware of the fact due to the lack of evidence, proof, justification, etc. Whether it is knowledge? Apparently not. And speaking formally, model logic offers a limited formalization of knowledge. It captures the notion of a true belief, because we indeed now, in addition to the usual Boolean based or maybe some other based logic, we have a special marker, so unary connective, which is called modality, which marks certain propositions as known. So knowledge is regarded in the model logic as a true belief, but there is no justification in the model logic of knowledge, traditional, and hence a principal gap between mainstream and formal epistemology, because as we mentioned, in mainstream epistemology, since Plato, justification was in the heart of discussion. And the formal models of knowledge, there are no such an object at all. And what kind of deformations? So there are several defects in the traditional model of knowledge. The obvious defect is well known as logical omniscience. The basic principle of model logic, as a knowledge belief, it says that the box marks knowledge. So it says that if it is known that A implies G, and it's known that F, then G is known. And at each world, the agent is supposed to know all logical consequences of his and her assumption. So together with the model language of model logic, we swallow the principle that each agent knows all logical consequences of he and her assumption, which is totally unrealistic in the real world. For example, each agent who knows the rules of chess should know whether there is a winning strategy for white. Or more close to the computer science heart, suppose one knows the product of two very large primes. In what sense does he or she know each of these primes, given that factorization may take billions of years of computation, even the most powerful machine? And the traditional logic of knowledge was not able to distinguish these things, because all these questions just collapsed trivialized. So it's known there was a trivial answer to all this. Less visible, but still even more fundamental defect is the failure of epistemic closure. It looks surprising, but the basic principle of model logic, that's one that's subtle a little bit, that the closure of knowledge under, deductive closure under modus ponens fails to fully represent the epistemic closure principle, which says that one knows everything that one knows to be implied by what one knows. And later on we'll consider the famous Kripke-Red Barn example, which really shows what's going on here. And what the justification logic does, I skip two millennia and more, and we go directly to the point. It adds justification into the language. Instead of adding box, what we do, we populate these boxes, which are the markers that something is known, with evidence of why this particular thing is known. So we end up with what is called the calculus of justifications. So the basic format is, instead of saying box F, saying that F is known, we say T column F, which looks familiar to people who do, say, types or typed languages and type structures. We can say that T has a type F. Or we can say that T, this is the list of possible natural, informal interpretations of this notation. T is a justification for F. of f for a given agent. T is accepted by an agent as a justification of f. There might be subtle differences between them. T is a sufficient resource for f. We can count it as the logic of resources as well. And f satisfies condition T, and so far and so on. Yes?
First two, they mention agent.
Yes.
But agent does not appear in this.
Because we start with one agent. We're present because it's just one agent. It's like in physics, at one electron in the universe. We do this theory first, and then we'll add, we'll multiply it. There will be, yes, we'll multiply the agent. So there's this one. So we started with one agent, and we studied this, the clean notion of knowledge for one agent, and self-knowledge in particular, but then we end up with that. So the basic justification logic, J is language, has then objects of two sorts, formals and justifications. And they're somehow connected. So the first contribution in this area is to introduce justifications as separate objects, as individual objects which have their structure. And for epistemology, this is probably this was already and has been and still is probably a pretty big leap, because to convince epistemologists that justifications deserve studies, they deserve to be isolated as special objects, and they have structure, it's a big deal. And it's still, the formal system is here, and hopefully it helps, and as well as examples, some of which I will present later. So there are objects of two classes, so justification terms or justifications, which are built in the usual mathematical or logical style from variables and constants, like polynomials are built from variables and constants, using two operations which are symbolically represented as plus and times. That's why sometimes they call justification polynomials, plus and times. Of course, we still have to define the operations, how the operations plus and times really operate. And then justification terms are free objects built from this atoms, variables, which will denote unspecified justifications, constants, which will denote very specific justifications for specific objects, and two operations plus and times. For the time being, it's just the set of formal objects of this kind. And formulas, it's the usual definition of a formula, which are built with new constructs if propositions, all propositions are formulas, and proposition variables are formulas, and there's a usual set of Boolean conjunctives. We consider the propositional case first, and there is a new construction, new constructor, formal constructor. So T, if T is a justification term and F is a formal, then T column F is again a formula. And as a result, we have formulas which have these columns inside in any depth. And since it's a constructor, it's unlike the type theory when all justification terms are outside and all formulas are inside. We really allow any mixture of these notions. In particular, let's read this one. It says that if X is justification of X, then C times X is justification for B. Or a more complex thing, if X is justification for A or Y is justification for B, then this particular term, A times X plus B times Y, is justification for A or B, etc.
You allow to nest.
Yes, that's the point. And that's the main difference from combinatorial logic. Well, there is some nesting. Well, there is nesting with respect to the Boolean conjunctives, but of course we allow nesting of terms. So it's TF may contain justifications in any depth itself. So that's why there'll be Taurus justification. So there is justification that something has justification, that something doesn't have justification. Or we appeal to specific justifications. And that's the point. We'll compare it later on. I don't remember whether I have slides on this, but basically speaking, the combinatorial logic, when I speak T is a type, has a type F. We may also regard it as a very special one layer case of justification logic. And in this case, the justifications are explicit, but there is no nesting. In model logic, there is an arbitrary nesting. You can build box upon boxes and in any combination with Boolean connectors, but it's not explicit. There are no justification in there. And what justification logic does, we allow both. It's explicit, so we carry on justifications, and it allows arbitrary nesting. And that's the point, and that's the theory which we provide with. And formalization of several paradigmatic examples show that this is an adequate approach. Well, logicians, they ought to be axioms, and here they are. So the basic justification logic J, so we just list the principles. So the standard axioms and the rules of classical propositional logic. So the usual logical rules are all applied here. So we're talking about some annex on the top of the usual, say, classical logic. And these new principles govern the behavior of sum and application. Probably application is more important, so it started, but it's more important, but it's also more familiar to people in this area, because basically what it says, if T is a justification, that F implies G, and S is a justification for F, then T applied to S is justification for G. This corresponds to well-known just Brouwer-Haitink-Kolmogorov condition, and that was the main idea of type theory of lambda calculus. We carry on these terms, and if there is a certain match of term types, term T has a type F implies G, and S has type T, then T applied to S has type G. This is a functional reading of it, and we provide an epistemic reading of the same principle. So the justification for implication F implies G is a construction which, being applied to any justification of the antecedent to F, provides us with the justification for the succedent. That's the idea. And this is a very traditional formulation of the application principle. And the plus, it's a sum of the choice function. There should be some intelligent comments there. So sum pulls together S and T without performing any epistemic action. For example, it basically says if S is a justification for F, then we can pull it together with some other justification, doesn't spoil it. You may regard it as kind of monotonicity requirement. So if you have justification, then adding, putting in, throwing in some other more justification doesn't really spoil the fact that this what we have at hand is a justification for F. And the same from the other side, it's a symmetric thing. So the usual thing is like chapters or a handbook, or there are 2 volumes. If F is a theorem which is proven in volume 1, so volume 1 has justification as a proof for F, then the 2-volume set has a proof of F. Or if the second volume has justification, so the proof of F, then the 2-volume set has a proof of F. That's basically the reading. And surprisingly, in order to match the expressive power and to exceed the expressive power, to capture the expressive power of model logic, we need this kind of non-deterministic choice function. With this at hand, we can really prove the theorems that what we do with justification logics, logic of proofs, is at least as good as what we can do with model logic, but we can do much better because we provide with explicit evidence. And the traditional model logic tool doesn't. It reflects very basic reasoning about justifications. There are still no principles which allow iterations, but they will appear later on. Because I wanted to keep things in this presentation simple. It was not historically the first system. The historically first system was LP, which had 2 more operations. Or at least, well, 1 more operation than special protocol about constant specifications, but we'll discuss it a bit later. So justifications are not assumed to be effective. So that's important, because it's if we add the effectivity principle, basically saying that T column F, if T is justification for F, then F holds the effectivity principle. It's like a reflexivity principle. This will capture represent knowledge more fairly, but not the basic justification logic J, which covers both effective and non-effective things. And this is important for applications. Yes?
What if you want, if intuitively, if you want to prove negation, what would be justification for negation?
Oh. If you want to prove that something is not justified, the formula is not true. Well, it's easy. You say that T is a justification for not F. This is. So if you find that F is not true, say that you believe that F is not true, you have to have a justification for it. And so the T column not F is a fair representation of it. If you want to say that something is not provable at all, so for no justification, then this language is not good enough. You have to combine it with the traditional model language. So the model language is good for stating negative claims, that something is not known. This language is very good for stating positive claims. And the real system, which I will advocate here, which first appeared in our joint paper with Lena Nogina, the real answer is we have to combine the model language with justification language. Because sometimes it's convenient to provide a specific justification. Sometimes we don't care. Or we want to say blanks, we want to say statement that something is not justified at all. For this with the specific justification, we're allowed to say that this specific thing is not justification for this one. But we're not able to say that something is not justified. We need to have box language in there. And this is also done. It's also one of the avenues of research. The joint language is the true answer, indeed, yes. But without justification, it's also not a complete picture. Good, very good question. Any questions? So this logic and this language is already good for conditional statements. If X is justification for A, then T of X is justification for B. In all the epistemic model language, you would say box A yields box B. But it's like assuming that box contains some existential quantifier inside. You'd say, if there is justification for A, then there is justification for B. But we're like in a Skolem style presentation, where explicit our language says that if X is any given justification for A, then T of X, a specific term, is justification for B. This is our language, and this, if you wish, that's the contribution to the formal epistemology is right here, basic. We also need some sort of a priori justified knowledge. So, and this is the special chapter about constant specifications. We have to assume that certain things are known ex officio. For example, propositional axioms. For example, there's the conjunction law. A and B implies A. We assume it's known, but we want this to be internalized. So not only we assume that this thing is true, but also we use the constant to denote some justification for the thing, or a proof, if you wish. And this new axiom may also assume justified, so we add it on the top, that there should be justification that this thing is justified, etc. These kind of constant specifications are part of the logic system, but it's part of the description, so we're free to add them or not to add them. And for studies in formal epistemology, when we want really to capture the case of Cartesian skeptic, for example, where nothing is assumed to be justified or known a priori, then we just leave the constant specification empty. And it would mean that all your statements, what you'll be able to say is that there are conditional statements. If something is justified, then something else is justified. But probably more mainstream approach, or at least for a mathematician, would be to assume that certain axioms are known or justified, and then to build from this some conditional statements about justifications. Another new feature which appears here, it's internalization. Technically, it works for sufficiently rich constant specifications. For example, if we assume that all propositional axioms are known at any depth, or they're justified at any depth, and this is one of the sufficient conditions for the thing to work, then internalization holds. Basically it says that f is derived or known by some sense, then t, we can extract the specific justification for f. Just look at this term style. So if f is derived, then t column f is derived for some specific t. The traditional model logic uses this as an implicit version, as a necessitation rule. It says that if f is derivable, then box f is derivable. So if we somehow established f, then we can be sure that f is known. And and our form of internalization is an explicit form of necessitation rule. By the way, first guessed by Gödelin in one of his lectures in 1938. This is an example of reasoning. Probably we'll just go to for the sake of time saving, go to the second example. This example was shown as a legitimate linguistic construction, so some slides back. Now we claim that this thing is just derivable in the basic justification logic. Well, it basically says that if x is a justification for a, y is justification for b, then this complicated term, ax plus by, is justification for disjunction a or b. How we do this? Well, and what is a and what is b? A and b appear in this derivation as a result of constant specification. Somewhere inside deriving this thing, we have to specify a. In particular, our a will be the constant which is the proof of this logical axiom, a implies a or b. And b is a constant which is a proof or justification for this logical axiom, b implies a or b. And then with these two, equipped with these two constants a and b, what we do, we distribute this a, the knowledge or the belief through implication by using one of the principles, the application principle. It says that if x, from 1 we deduce that if x is a proof of a, then a times x is a proof of a or b by application modus ponens. And we do the same for b. And we end up having something that it says that if x column a, if x is justification for a, then something is justification for disjunction. If y is justification for b, then something else is justification for disjunction. In the usual model logic, there is no distinction between these justifications. They are just markers, they're just labels. And they're automatically unified. In our case, there's no automatic unification. Since we care about specific justification, we need some reconciliation mechanism. And this is where sum goes into play. We relax both of these succedents to saying that the sum of ax plus and by really has justification for disjunction, and then we conclude that the disjunction of xa or yb really yields this particular disjunction.
Does it remain true if we replace disjunction in both places with conjunction?
I have to say, if this is, well, the term will be different, yes. The term will be different, yes, because we use different logical principles to justify it. But there will be some term in here, yes. It remains true, and it's even easier, but I picked this example because that's the one, it's probably the simplest one when the plus shows up. Because with conjunction we don't need plus, we can do with application only. So it's easier. But am I right that was the previous example? Oh no. It was the one-way example, yes. So it remains true if you replace this disjunction by conjunction in both cases, but the term will be different. I can show you, given time, how it works. Now, just back to epistemology, some rather well-known epistemological examples. So it's a Kripke-Red Barn example. Suppose an agent, or Henry or I, am driving through a neighborhood in which known to me papier-mâché barns are scattered, and I see that the object in front of me is a barn. Because I have a barn before me percepts, I believe that the object in front of me is a barn. However, our intuition suggests that I fail to know barn. So it's a belief, but I cannot know that's a barn because I can be easily mistaken the fake barn, the real barn with the fake barn for the real one. But now suppose that in the same neighborhood there are no fake red barns. So I notice that the object in front of me it looks like facade of the barn, but it's red. And so I know that the red barn is there. And this juxtaposition, where it's being a red barn, which I know entails that being a barn, which I don't know, is an embarrassment. So this looks like a violation of epistemic closure principle. This example would look more clear if we go to its formalization. Sometimes formalization z help. So the red barn example. So we consider two propositions. B is the object in front of which I see is a barn, and R, the object in which I see is red. And so B is the belief modality, which is not necessarily knowledge, but we'll see. So by observing the barn, I formally believe that this is that I see the barn. The object in front of me is a barn. This is belief, but not really knowledge, because I could really mistake it. On the other hand, when I have a, yes. If I see that the object in front of me is red, that from what I know it's knowledge, that it is barn and it is red. So we have the following condition. We have known, well, okay, we know the implication, and this implication is knowledge because it's logical truth. It's just logical axiom concerning conjunction. B and R yields B. And that's why it's known, because it's just the knowledge of a logical axiom. We'll assume that it is the case. So this is not belief, it's knowledge. Then we have a knowledge of the antecedent. We have knowledge that B and R takes place. But box B, at least this observation, is not knowledge. It cannot be counted as knowledge. It's not knowledge. And this was an example which shows that the model treatment of knowledge, when the Boolean treatment of knowledge doesn't really capture this the logical, the epistemic closure principle. Because we know the implication, we know the antecedent, but we don't know the antecedent. And the analysis, the answer why this happens is because the epistemic closure principle is formulated. The reason is material implication between them. Because, let me just jump back to this principle model. Yeah. This implication is material. It basically says that it basically forbids certain Boolean combination of truth values. It says it cannot be the case that this thing holds, and this thing doesn't. And Kripke showed us the case when this thing holds as well, and this thing doesn't hold. Because in the Boolean and material implication, it's just the condition of truth values. It doesn't show any connection between these three boxes. It's a missing thing. So it basically says no matter how we learn this, how we learn to believe in G, and how we learn to believe that F implies G and F, it cannot be the case that these two are true and this is false. And this Boolean approach to implication or material implication doesn't capture what we really, the informally formulated principle that one knows everything one knows to be implied by the one else knows. And the picture becomes totally different and, well, I believe much more transparent if we really do it with the justifications. Look what happens if we trace the justifications. So first we form the belief, by the first observation, we form the belief U that B is a barn. This is a belief but not knowledge yet. But this, we keep track of what this particular justification. Then we have a separate observation, V, which yields, after which we form the belief that B and R holds. And also we know by some constant specification, of course, that there is a general evidence that B and R yields B. It's just logical constant. From which we derive by application within the J, within the basic logic of justification, we derive then V, the fact that V is a proof or the justification that B and R takes place. Then A implied to V is justification for B. From which we immediately derive that A times V is justification for B, but not U. So the paradox really disappears, because when we really trace the specific justification, we see that in the first encounter, what we learned, we formed the belief U, whereas from the second encounter, we logically derive that the belief A times V for the same fact B. So actually we deal with the two different justifications for the fact B. One is factive, one is knowledge, A times V, and one is not knowledge, U. And this distinction can be made only within the framework of explicit justifications. Yeah.
B is belief, which is not knowledge.
Well,
how we justify belief, which is not knowledge? Different justification.
No, B is a proposition, and which happened to be true. But so we now B is a barn. B is really a barn. But when you observe that it's a barn, without paying attention to the color, misty, you see it looks like a barn, you observe it's a barn, you believe it's a barn. But you can be easily mistaken.
So this way you only speak about barns which are red.
Yes. And that's a trick in the Kripke example. It says that if we observe that that's a red thing, which is a conjunction of being barn and being red, actually, then you can, well, if you observe that it's a red barn, then you derive that it's a barn, and this is the correct conclusion. You really form a knowledge that the thing is a barn. B is a barn. But this knowledge which you form is combined from the knowledge V and knowledge A. And this knowledge is A implied to V. That's why you know that's barn, but not because of you.
So if you quantify, say, for all B, and that you begin with statement that all barns are burning, and now you say only all red barns are burning.
Well, you can squeeze this. What you're saying, you can form it here. Yes. So, but again, the basic message: if you track the specific justifications, you end up knowing what is knowledge and what is belief. Whereas if you do it within the usual model logic, then everything collapses into boxes. There's no distinction between them. I'll show you one more example, which is probably even more visible than this one. So the moral here, justification logic offers a better formalization of the epistemic logic principle. It says if S is a justification for this thing, and T or T is justification for F, then S implies to T is justification for G. We don't claim that other justifications, other things may be justification for B. We claim that only this particular one is. And there's a clear functional dependence between the justifications for the antecedent and the justification for the conclusion. And that's again what the machinery which justification logic offers to the thing. The formal notion of model, so we can upgrade the notion of Kripke model by adding justification into the picture, but probably this makes sense if the audience is really familiar with the notion of Kripke model, which I do not quite assume. For the time being, we can stay here, but let's go to some other example, which is probably more useful at this point. It's Russell's example of 1912, also rather well known. And we use it to show that there is so-called induced factivity principle. But let's read the story. If a man believes that the late Prime Minister's last name began with B, he believes that it's true, since the late Prime Minister was Sir Henry Campbell Bannerman, which was true back to 1912. But if he believes that Mr. Balfour was the late Prime Minister, he will still believe that the late Prime Minister's last name began with B. Yet, this belief, though true, would not be counted to constitute knowledge. This is one of the examples when the true belief is not necessarily knowledge, even if there is a justification for it, because this justification may be not true. Okay, but let's look formally what happens here. So again, here B, the proposition that the late Prime Minister's last name began with B. So B is a proposition. W is the wrong reason for B, and R, B, the right reason for B. So in the Russell example, we have the following small database, which says that we have the wrong reason for B, we have the right reason for B together in one system, and the right reason for B is also effective, because if there is a right reason for B, then B really holds. And that's a logical description of what's here in the story. Paradoxically, from these assumptions, we can logically deduce the effectivity of W as well. Because, look, from second and the third, we deduce B. And since we deduce B, then B follows from any assumption, as logicians teach us. And in particular, it follows from W column B. So it formally can derive the claim that the bad one is also effective, which is called, this is the effect of induced effectivity. I'm chasing two ducks in this example. First, to show that we can handle different, this approach can handle different justifications for the same true fact, or for the same fact. One right justification, one wrong justification. This is something which the usual model logic doesn't do. Because if you look at the same database from the prism of the usual model logic, then the whole thing collapses. It says, box B says that B is believed, and belief in B is effective. So if there is no distinction between justifications, then the whole story collapses. There is no analysis, a formal analysis of this possible in the traditional ways. So, so the first story shows that we really have now a mechanism of tracing justifications and distinguishing good ones from bad ones. And for example, how can we distinguish them in this case? Because both of them are effective. So from this database, we can derive that W column B yields B. So the same as we had for R. But the difference is that if we, the only derivation of this fact uses the fact that R is really effective justification. And so if we throw it out, or we'll say that we can show formally, using the formal models at hand, the mechanism which we developed, that from assumption that the wrong assumption about the wrong justification from B, and the fact that something else is a good justification for B, but without assuming that the good justification, we cannot establish the effectivity of W as well. So we can really, using formal methods, we can sort out wrong justifications from right justifications. And it reminds me also of the story which I learned about reading and watching something about Watergate story. When the respectable newspapers, they publish a news only if there are two independent confirmations of this news. Because one confirmation is not good enough. They need, and the trick point is here what's independent. And this is the case when you can formally distinguish what one justification is independent from the other. Sorry.
I'm sure that what was proven. So let's see, you have a justification for B.
Wrong one.
No. You derived B.
Yes.
Using R.
Yes. Okay, like here, yes.
Right, you derive.
Yes.
Then you derive the fifth formula.
Absolutely, yes.
So if you honestly build the justification which comes from the proof,
Yes.
it will be more complicated than double. It will have
Absolutely, yes. So this example is the wrong example. We just, the purpose of the example to show that this kind of wrong conclusions should be avoided. Can we rule them out?
Which is
This is a bad thing which I want to rule out. And the message here is that our mechanism, along with the model theory, allows us to rule this out as the wrong thing.
But even here, if you get in 4,
Yes.
you get, let me see, in 3, you
Yes.
get B.
Yes.
But B, you don't get B for free.
Exactly. There is external justification which we carry on.
Right.
Absolutely, yes. And again, my point is that I'm not selling this particular example because it's a baby example. What I'm selling the language. I'm selling the approach. That now with the justification of the picture, we're capable of asking the right questions and answering the right questions, because this is not just a raw idea that we have to build something which keeps track of justification. It's a developed logical fields, the formal field with model theory, proof theory, and a lot of algorithms which are complexity bounds. All the basic work is done here. We have this small theory of how to trace justification. That's what I'm saying. But you're absolutely right. What we have to do is to keep track of, to internalize the whole thing one step down or inside, and then we'll see the difference. But the basic mechanism, the mathematical tricks we know will be the same as derived here. Yes. And this is the formal model which shows how to distinguish one from the other. And this is an observation which shows that the usual model logic just fails to distinguish the whole thing. The whole phenomenon disappears. So a little bit more about relations between justification logic and epistemic model logic. So the usual model logic is justification logic plus forgetful projection, if you wish. I'm wrapping up. And the justification logic may be regarded as epistemic model logic plus realization mechanism, because there is a big realization theorem, the foundational theorem, which says that there is a certain duality between traditional model logic and justification logics. If you take justification logic, if you forget all specific justifications, we replace them by empty boxes, you'll get exactly the usual model logic. This is an easy thing. This is an easy start, because justification logic is a more rich language. Going from rich language to poor language is normally easy. But the trick theorem is that if you have a derivation, the proof in the usual model logic, there is a coherent way to recover justifications inside all the boxes there. And this is a trick theorem which uses some rather sophisticated mechanism in proof theory to prove. But now we have some range of algorithms how to do this recovery. It's so-called realization theory. And that's the core of the story. So F is known, F is an adequate justification. So there are some foundational consequences. So now remember that we started trying to characterize knowledge following Hintikka and others. And F is known as something, if F holds in all possible worlds. And now we can say that F is known if F has an adequate justification. And this is a stronger assumption, because if it has an adequate justification, then of course it holds in all possible worlds. But it's more than that. It's a justification which should be at hand. And particularly it allows us to trace individual justifications and to take into account the complexity of justifications. So now the concluding slides. So what does justification offer? It adds along its space mathematical notion of justification to formal epistemology, making it more expressive. We now have a capacity to reason about justifications, simple and compound. We can compare different pieces of evidence pertaining to the same fact. We can measure the complexity of justifications by the size of term, maybe with weights. thus connecting the logic of knowledge to rich complexity theory. And justification logic provides a novel evidence-based mechanism of evidence tracking, which can be a valuable tool for extracting robust justifications from a larger body of justifications, which are not necessarily reliable. And successes, there is a solution of Gödel problem in the old reincarnation of what's known as logic of proofs. It's a very specific sort of logic of justification logic. The faithful formalization of Brouwer, Heiting, Kolmogorov semantics for intrinsic logic. A new take to the logical omniscience problem, which is now, which we discussed, in particular in the joint paper with Roman Kuznets. We consider a logical omniscience problem as the proof complexity problem and established that the old model logic representations, model-based representation of knowledge is indeed logical omniscience, whereas evidence-based representation of logic is not logical omniscient. Yep. And that's the one, yes.
Why not? You keep deriving things and always build justification.
Yes.
So you know infinitely many things.
Well, in any finite, yes, you know infinitely many things potentially, but in any specific time you observe a finite thing. It's like a Turing machine. Of course, you can compute infinitely many inputs and outputs, but in a particular thing, the configuration, there is a specific configuration on the tape.
Can you comment on many agents?
Yes, many agents. There are 2 or 3 papers already written and published about many agents, and maybe in this context, I would mention the third operation of justification. It's called proof checking or justification checking. When an agent gets justification, it's supposed to be able to check it and to verify that this particular T is a justification for this particular F. And in the context of many agents, there's a variety of choices. The basic mathematical theory is the same. It's like building Lego from existing blocks. But still, the interplay principles, we can represent that one agent is able to verify some other justification, but not the other way around. And a certain variety of these joint principles have been considered, and we have mathematical treatment of it, like completeness theorem, complete axiomatization, and several examples how they work. And I can give the references, but there are a couple of basic papers already written and published known about the several agents. Yes. And yep, I think that's enough for the core talk.
Thank you.